Hello, in this short video I'm going to be going through 3 additional practice problems that we did in class about how to do these problems that use force and the motion graphs together along with the Fu equals ma equation. So this is just a few extra problems to help get you in shape for the quiz on force diagrams and the motion graphs. And in fact, specifically here we kind of just use the velocity versus time graph because that's the most common and most useful motion graph that we have. So this first problem, it says a 2 kilogram object accelerates uniformly from rest and covers 100 meters in 5 seconds. What is the magnitude of the unbalanced force Fu for this object? And so looking back at kind of our diagram here, I've given you some information about its motion. I told you it accelerated from, I told you it was accelerating, I told you the distance it covered. So we're kind of going to start out with the motion graph side of this. And then actually we don't even make it over to the force diagrams because I just asked you for Fu. So we kind of go from the motion graph stuff just to finding out the Fu, and we don't even get over to the force diagrams because I didn't ask you anything about the forces directly, just about the unbalanced force. So starting this out, I'm going to make an example of my velocity versus time graph here. We've got velocity and time. And this is the basic one where it's accelerating uniformly from rest, and so we're just going to start off with it there. All right, some things that we know here. It says it traveled a distance of 100 meters. Distance traveled is the area. All right, so the area of this triangle is 100 meters. We also know that it happened in 5 seconds. All right, so that time there on the bottom is 5. What we can find from this is we can use the relationship that we know for this side here. This is our change in velocity to figure out what the acceleration is. In fact, if you're on top of things a lot, you know that this change in velocity equals the acceleration times time, which in this case, since we know that t is 5, acceleration times time is just 5 times our acceleration. All right, and we can just come up with it that way. And so we've now got both sides of the triangle, and this is a pretty slick way of doing this problem. We know that 1/2 times 5 times 5a. All right, those are our 2 sides of our triangle. And we're finding the area here. Oops, that should be a lowercase a. We know that that equals 100. So we simplify this down, and we end up with 12.5 a equals 100. Divide both sides by 12.5, and you get that a equals 8 meters per second per second. Okay, so I know that it's a little bit tricky there. You could have solved for the change in velocity and done it algebraically, and then just done change in velocity over change in time as well to get acceleration. Whatever way you do it, though, hopefully you can get it so that you find that the acceleration equals 8 meters per second per second. All right. Then after that, we can plug things into the Fu equals ma equation because we have Fu equals the mass here is a 2 kilogram object, right? And oops, I'll write down Fu equals ma. All right. And so that's a 2 kilogram object, right? And the acceleration is 8. All right, and 2 times 8 equals 16. And since it's a force, it's the unbalanced force. Forces have units of newtons, and so 16 newtons is our final answer there. So this one is just asking us to figure out what the unbalanced force is, and we'll leave it at that. This is a pretty short, direct problem. It actually doesn't use both sides of this entire process here. Really, we just did the motion graph, and it gave us Fu. In the other problems that we'll do, we'll be going all the way across this entire thing. So in this problem here, it says that we have a 10 kilogram box and it's released with an initial velocity of 25 meters per second. It says it slides across the floor and slows down to 5 meters per second over the course of 4 seconds. Assuming there's no forward force in the box, make an FBD and find the magnitude of the friction force. So in this one, just again to give you kind of the general process of this, it seems like it's giving us a lot of information about its motion. It says it has an initial velocity of 25 meters per second, and then it slows down to 5 meters per second over the course of 4 seconds. That's a lot of motion stuff, all right? And then it's asking us, in the end, it wants us to find force stuff. And so what we're going to do if we're looking at this process here is it's giving us motion stuff here, All right, and then we're going to use that motion stuff and get it to take us over to Fu equals ma. We find the acceleration. The whole point here is to find the acceleration so we can plug it into Fu equals ma. And then once we use Fu equals ma, then we can go to the force diagram stuff. All right, so we start with motion graphs here, and then we go to Fu equals ma, and then we go to the force diagram. So again, we do that because it seemed like it was giving us a lot of information here about the motion, and then it asked us for force stuff in the end. So we're going to do motion stuff first. So I'm going to create a velocity versus time graph here. This one is not our most basic one because it says it has an initial velocity of 25, and then it goes down to 5. All right, so it starts here at 25, and then it goes down to 5. All right, it says that happens over the period of 4 seconds. All right, and so some people on this, they look at it and they start like boxing in shapes and filling in things and finding the area and things like that. You don't have to do any of that because all we really want out of this process is we want the acceleration, so we can use the Fu equals ma equation. All right, we're trying to get to Fu equals ma, which means we want the acceleration here. Acceleration equals the change in velocity over the change in time. All right, it's the slope of the velocity versus time graph. Change in velocity here, it goes down by 20 meters per second over the course of 4 seconds. And you calculate that and you should get -5. All right, acceleration has units of meters per second per second. So that is our acceleration. And then when you do Fu equals ma, you get the mass here is 10, the acceleration is -5, all right, and you end up with -50. This -50 for the Fu is kind of confusing, and I'll explain kind of what that means here when we make our force diagram. So to make the force diagram, you got to think about the forces acting on this. We've got a gravitational force downward. It's 10 kilograms, so that means it's going to be 100 newtons for our gravitational force. All right, we also have a normal force on this, Fn. Because it's not accelerating in the vertical direction, we know that this is also 100 newtons, and those balance out with each other. All right. The other thing we have here is a friction force. Now, we didn't say what direction it was moving, but we're going to assume that if it's moving in the positive direction, that it's moving to the right, which means that I'm going to put this friction force off here to the left. There's two ways that we generally know that the friction force is going to the left. One reason is because friction resists motion, usually, all right, not always, but friction usually resists the direction that the object's moving. So if the object is moving here to the left, friction is going to go to the right, all right? The other way that we know that friction is to the right here has to do with this -50, all right? That -50, the negative really just means to the left, all right? And so when I write it in here, I'm just going to write 50 newtons, all right? And the reason that that works out is because the negative is implied when I show that it's going to the left, which is in the negative direction. These are just things that I think mostly it makes sense in your minds when you think about these things, but the negative signs can be kind of weird, and they pop up at some different times. But as long as you have the general idea here, I wouldn't sweat the negative sign too much. As long as you kind of have the forces in the right directions on the diagram, I think you should be good to go. All right, so here's the last problem. It says a 1,000 kilogram car drives with a forward frictional force of 2,000 newtons and an air resistance of 850 newtons. I said, assuming the car started from rest, found how long it takes the car to travel 250 meters. So on this one, it's a little bit different because on this one now, I'm giving you a lot of information about the forces. I told you its mass, which gives you the gravitational force. I told you it has this friction force on it. I also told you the value of the air resistance force. And so I'm giving you a lot of stuff about forces. And that's where we're going to start this problem. And then in the end, I ask you stuff about its motion. I say, how long does it take for it to travel 250 meters? So we're actually going the reverse way in this process than we have been before. So here we're starting with force diagram, right? And we're trying to find Fu from that. And then we use Fu equals ma. And then once we get here and use Fu equals ma, that gives us the acceleration. And then we can use that for the motion graphs. So we're actually going kind of in the reverse order on this problem because we were given information about the forces, which allows us to make the force diagram. And then we do the motion graph second. Okay, so here we go. We'll make the force diagram. Forces on this one, we've got Fg going down. All right. It's 1,000 kilograms, so that means it's going to be 10,000 newtons for its gravitational force. It's not accelerating in the vertical direction, so we know that the normal force is going to equal the same thing as the gravitational force. All right, because those are going to be the same. Then the other forces on this is a little bit confusing because I said it has a forward frictional force on it. Okay, I just said in the last problem that friction almost always resists motion. Well, in the case of like a car moving forward or a person walking forward, friction actually has sort of the opposite effect. What's happening here with friction in a car is the wheels are spinning and the friction between the tires and the road are what pushes a car forward. So there's a frictional force between the tires and the road, and that's what ends up pushing the car forward in this case. I told you that is 2,000 newtons for the frictional force. All right. There's also an air resistance force as this car is driving forward. All right. The air resistance force, FAR, I said, equals 850 newtons. All right. And that's going in the reverse direction. All right, because air resistance fights against motion. All right, and so now you've got this general force diagram. The top and the bottom cancel out with each other. All right, the left and the right do not completely cancel out. There's more on the right than there is on the left. And so we have an unbalanced force here. If you take the 2,000 newtons and you remove the 850 that are going the other way because they cancel out, we end up with a total unbalanced force here of 1,150 newtons. All right, then we can use our Fu equals ma equation, Fu equals ma. We plug things in here. We know that Fu is 1150. The mass is equal to 1,000 kilograms. The acceleration is what we're trying to find here. We solve that and we get acceleration equals 1.15 meters per second per second. All right. Now that we've got acceleration, we can make our motion graph. All right, so we're going to make a velocity versus time graph here. It's the same basic one that we have. It's starting from rest, and it's accelerating in the forward direction. All right, so it's this basic one here. On this one, this is a case where we know the acceleration and we know the distance traveled. All right, but we don't know anything else about it. The distance traveled is this area here, 250 is the area. But we don't know anything else. So this is the general way that we approach the problem if we know the distance traveled and the acceleration but nothing else. We say, all right, however much time has passed, if we put that there, we know that the change in velocity equals acceleration times time. All right, and we actually have the acceleration as 1.15 t. All right, so the acceleration is 1.15, and then at would be 1.15 t. And so we have now both sides of this triangle, and we can set up an equation here, an algebraic equation, to figure out what t would be, because we know the area of the triangle is 250. So area of the triangle is 1/2 base times height, 1/2 times t times 1.15 t. Equals 250. The left-hand side of this equation simplifies to 0.575 t squared, all right, equals 250. Divide both sides by 0.575 and then take the square root, and then you should get that t equals 20.85 seconds. All right? And that is the answer there. Okay, so hopefully you've seen this type of problem enough times that you're kind of getting used to the way that it goes. I give you some information. You use that information to either create a force diagram or to create a velocity versus time graph. Then you figure out what you can from that. If you start with a force diagram, you're trying to get Fu, so you can plug it into Fu equals ma. If you start with a velocity versus time graph, you're trying to get acceleration, so you can plug it into Fu equals ma. All right, and then we go to the other representation after that. If you're struggling with these problems still, make sure that you come in and talk to me.